All right, so welcome everyone. For those who are regular attendees from Cohere for AI, welcome back. And for the remaining, welcome to Cohere for AI. Make sure to join the Discord if you want to continue discussions, things like that. So our today's guest is, hopefully I don't mispronounce your name, so just feel free to correct me. So our today's guest is Zhijing Jin, and she is an incoming assistant professor at the University of Toronto. She finished her PhD at Max Planck Institute and ETH. She works on socially responsible NLP by causal inference. Specifically, her research focuses on causal reasoning with LLMs and causal methods to improve robustness, interpretability, and fairness of LLMs, as well as causal analysis of social problems. She has received not one, but 3 Rising Star Awards, 2 PhD fellowships, and you might probably have seen many of her works published at top NLP and AI venues. She's also very active at the ACL channel. So welcome.
Awesome. Thank you so much for the warm introduction. And I'm glad to interact with this nice audience today. So today my talk will be on, can LLMs achieve causal reasoning and cooperation? Also during the talk, if you have any questions, feel free to interrupt so we can have a vibrant discussion. Cool. So we will start from the motivation. Probably a lot of us have seen many NLP talks, and mainly nowadays LLMs are very popular in that they do not only revolutionize the NLP field, but also they can be applied to many domains such as code generation, robotics, decision-making, computational social science, and so on. However, a key problem before we make all the bridges between NLP and many others is a reliability problem. For example, if we see some error reports of such LLMs, we might have seen this one on LLM will give suggestions on putting glue into pizza or eating rocks. So if we look into the exact type of error pattern of this eating rock example, it was originally a Google query trying to trick the LLM, formulated as how many rocks should I eat? And then we know that there is AI generated overview these days. So we'll say, according to UC Berkeley geologists, eating at least 1 small rock per day is recommended for health. And if you really open the search pages, you also see there are certain websites claiming these type of things. However, is eating rocks really a cause for health? So what we need LLM to do is basically to fill in a gap. If we look into its current working mechanisms, then LLMs are pretty good at direct generation, such as what's the capital of France? It's Paris. Or searching for websites and using RAG to complement its answer. In this case, it does look into websites about rocks and health and quote it back. However, the major problem here is, what if the direct generation has hallucination, and what if the websites could be wrong themselves as well? So a rising trend that we have seen here is basically adding in some simple math and data science to support every claim instead of just quoting the text. So if we look into this idea, like maybe ideally we should survey the number of rocks people eat per day, their health condition, trace longitudinal studies, or have certain sufficient data between the information of eating rocks and health. However, just adding such correlational analysis would also be not suffice. Imagine we have this example of the correlation between chocolate and Nobel laureates, the number of Nobel laureates per country, then if LM could be a great data analyst and plots this data, gets the correlational factor, it still didn't tell much causality about whether eating a bit more chocolate will raise the Nobel laureate number in your country. Moreover, this problem is probably pretty serious in that RAG will also be likely to tell us a similar answer supporting eating chocolate, as many websites also are in support of such claims. So the gap we identify here is maybe all of these three methods that we want to rely on could go wrong. And the further skill that we want to add to LLM would be about causality. So basically, how does causality differ from correlation or simple data analysis that we illustrated before? So if we have the data between chocolate and Nobel Prize, then having this correlational plot is basically something about the past. We interpret that this target phenomenon has high correlation with all these indices. However, if we want to act towards the future, now given all the data, I want a meaningful action to really increase the Nobel Prize laureates in my country. What should I do? In that case, we need a strict sense of causality, and we need some variables to change and some variables to react towards that change that we perturb. The importance of causality can also be seen from ancient Greeks, such as Aristotle has highlighted that we do not have the knowledge of a thing until we have grasped its why. That is to say, its cause. Going back to this example, basically correlation is about predicting the relationship between two variables, whereas causation is about changing and expecting corresponding differences. To capture certain phenomena, we introduced a causal graphical model as the formulation for causality. Basically, we consider a graph G consisting of a set of vertices V and edges E. The vertices are random variables, in this case X, Y, Z, and the direct edges are causal link, such as A causes B, X causes Y, but in the meantime, Z causes X and Y. Making it into the real example, the previous question about chocolate and Nobel Prize basically questions the existence of this edge directly from chocolate to Nobel Prize. However, an underlying problem could be that maybe there exist confounders, such as socioeconomic background of a country, that leads to the chocolate consumption and also leads to the Nobel Prize situation. To conquer this problem, we can see many previous work in the machine learning field, a lot of them led by Benha Shokov, my PhD supervisor, and Yoshua Benjo, towards causal representation learning and causality for machine learning. With this context, my contribution from PhD and this time forward is to curate the research agenda on causal NLP, namely to understand and improve causal reasoning in natural language processing models. We mainly address two types of tasks inspired by causality literature. The first task is about causal discovery, namely what variable affects what other, such as given X, given Y, does X really causes Y? And the other case is about quantification, namely causal effect reasoning. If we already know the causal graph is as follows, then what's the strength of the influence of X on Y? They could correspond to different natural language examples. For the first one, it can be, given that we have read a lot of articles of tech company CEOs are college dropouts. Does it mean that dropout causes job success? For the other case on causal effect reasoning, it could be about how much does COVID vaccination increase the survival rate? And they also correspond to two recent papers of mine. One is the core to cause, and the other is Cladder, climbing the causal ladder. We will cover them one by one in this work. And we will also highlight that they all fall under the category of reasoning for LLMs. And that is a really heated topic in the NLP field, in that many leading scientists disagree on whether chatbots can truly reason or not. Whereas where the reasoning is a skill defined as carefully and logically solve a problem through a series of discrete steps, each one building on the next. So bring this spirit forward, let's look into whether LLMs can do causal reasoning. The first task we look at is whether they can infer causation from correlation. A motivating example of this case is a very famous case in the field of causality. But let's imagine that we have a common sense data set and a lot of news articles on this summer, we see a surge in ice cream sales, and also the rate of shark attacks sharply increases. Then what should the model infer from such statement? Well, hypothesis one is maybe ice cream makes us taste better. Hypothesis two is that it's about getting warm being a confounder. So getting warm can lead to people eating more ice creams and also leading to more swimming in the sea, thus more shark attacks. Putting everything into a causal graph, if we label them as A, B, C, D, then the variable A getting warm leads to B and C, and then C further leads to D. What's problematic with the initial statement on whether ice cream causes shark attacks is that here is a connected causal graph of all the four variables A, B, C, D. And as long as they're connected, there's a high chance that any pair of nodes may be correlated. However, we cannot derive direct causation because causation is defined in terms of the causal graph as that, let's say in this case, from A to D, there is a directed path without any reverse directions in the middle. Whereas from B to D, we have to reverse one arrow and then go along a directed path. So B is not a causal cause of D. Moreover, apart from denying the necessity of any node causes another node in a related causal graph, we could also go one step further to infer causality, such as in this case, C should be a cause of D. And we are able to infer that by either intervention, let's say, hypothetically, let everybody just swim in the swimming pool, then we will no longer see any correlation at all, and then thus refuting it. Or we can apply the causal discovery methods, which enables us to also just take correlational data, but deduce valid causal relations. To structure such tasks for NLP, we introduced the core to cause dataset on correlation to causation inference, where the input is correlational statement, such as, suppose we know that A correlates with B, and can we infer that A causes B, where we expect the output to be the judgment of a causal relation, such as yes or no. And in some other cases, let's say this is a famous phenomenon called collider. So if you see the relation between three variables as A correlates with B, C correlates with B, however, A is independent of C, then this relation between A and B must be interpreted as causal if you follow the causality literature. So in this case, we will actually give an yes to the answer. And we basically extensively included all the possible causal graphs with a given number of nodes. So roughly in our data set, around 20% of the answers are yes, in the case where we can get a definitive causal conclusion. And our data set can be accessed on Hugging Face with 200K samples and 1K test data and 1K dev data, as well as the GitHub is open source. So if we look into the performance of LLMs on this issue to address the beginning question of whether LLM can achieve such reasoning, we see that a random baseline due to the label distribution gives 20% F1 score. Adding in the open source models such as Llama and Alpaca, we see the performance increase a little bit. And also trying the GPT-4 up to last year, we see only 29% performance on this task, which is also far less than satisfying. Lastly, we also deployed quite a lot of natural language inference models, such as BART, fine-tuned on EMNLP, and many others, which receives a relatively high off-the-shelf performance. This is just a quick overview, and we will also introduce another causality task before we dive into some modeling suggestions or takeaways for future work on causal reasoning. So covering the other branch, the other type of causal effect reasoning, we look into a follow-up study on climbing the causal ladder, assessing causal reasoning in large language models. So as we mentioned, now we will move from qualitative judgment of the relation between two variables to a quantification of such relation, such as, is it positive? Is it negative? How large is the size? An example we have from real-world data on Israel 2021 COVID cases was that actually in the statistics, we see that vaccinated people are more likely to develop severe cases of COVID. However, does it mean that the overall causal effect of vaccination is negative for health? Here, to address this problem well, again, we plot it as a causal graph where vaccination is a cause for severity. And behind that, there might be a confounder, namely vulnerability. So vulnerability affects both variables in the following way. An originally more vulnerable group can have higher vaccination rate as they go to vaccination stations more often, but also higher severity rate because they're originally more vulnerable. So the right approach is actually to separate the vaccination effect for each level of vulnerability among the patients. And then this action is called confounder adjustment. So adjusting for different types of confounders values, and then aggregate the causal effect based on that. We obtain many similar questions on different ways to adjust for the causal effect and collect a set of 10K questions covering prototypes from standard causality books, such as Julia Pohl's Causality, Causal Inference in Statistics, Elements of Causal Inference by Jonas Peters, Dominic Janssen, and Bernhard Schokow as well. And each of the example questions in our data set is like, we provide the causal graph, we provide, and where we mention such as physical vulnerability has an effect on what, vaccination has an effect on fertility. However, you see the statistics and the conditional probabilities like this, then can you conclude that vaccination leads to an increase or decrease in the survival rate? And we simplify the quantification question to positive and negative for the effect value. And therefore, it's again easy, like feasible for us to evaluate LLMs in that they will produce yes or no answers. Yeah, looking at the correct way of solving it. So we do expect that ideally, if it's human causal inference scientists seeing those questions, then they will perform corresponding, let's say, confounder adjustment or many other estimation methods. Whereas here, the key question is, if we switch it to LLMs, can it perform as good as humans? We also colloquially call it the causal Turing test, in that can LLMs distinguish from human performance on dealing with these causality tasks. Looking into the actual performance that we evaluate, so because we're able to design the positive and negative answers half-half, so the random questions are 50%, as the labels are uniformly distributed. And then from all the way to GPT-3, including many of the open source models, their performance is still close to random. Whereas adding instruction tuning, different versions of instruction tuned models, they have an increase in such causal reasoning skills. However, when we further add the two versions of ChatGPT, namely GPT 3.5 and GPT 4, then we see an initial drop in GPT 3.5. Some reasons could be that it optimizes for the chat friendliness and customizes the user interface. So there was some sacrifice on scientific reasoning skills. But then moving to GPT-4, it demonstrates an overall improvement on scientific reasoning skills, including causal reasoning. So we see an improvement until 62% accuracy. However, the next question becomes, can we expect something even better? So what we look into here is a causal chain of thought, causal COT prompting, where we give the question, the same input question to LLMs, but instruct it through a 5-step pipeline to solve it. The first step being parsing the causal graph, and then the second one is about formalizing the query. Is it about the average treatment effect? If so, then from which causal variable to which effect variable? And then translating things into formal notations, as here, we should compare the expected value of vaccination given that we perform an intervention on like expected value of survival rate, given that we perform a due intervention on the vaccination being true versus vaccination being false. And then we will try to estimate this value by using all the statistics we have at hand. In this case, it's like the probability distribution of vulnerable people is half of the population. The probability distribution of survival, given that the person has taken the vaccine, is following, and so on. Then it's about conducting formal causal inference steps, such as aggregating the statistics according to different levels of vulnerability, which is one of the most popular methods in due calculus to obtain this causal effect by only observational data. And also there are methods such as counterfactual prediction in addition to due calculus, all fall into the statistics domain of how people solve these questions. And then ideally, they should also perform the right arithmetics once we lay out the formula correctly before deriving at the final answer. Given this, we see that adding causal COT to GPT-4 leads to an 8-point improvement in accuracy for the models. And when we evaluate human graduate students on the same task, then the rough performance is 80%. So this is an effective step to bring the LLM performance closer to human scientists. Lastly, in terms of the takeaways from the entire causality section, so our insight is that we really want to treat future problems as a scientist, given LLM's existing abilities on direct generation, RAG, and so on. And the right way to solve the problem is to understand it, formulate it, and ground it in formal expressions. The solution towards that will mainly be about designing a set of structured steps following how human scientists solve them. And ideally, in the future, we also want LLMs to connect with tool use, calling code or API or Mathematica and so on to deliver scientifically grounded results. Yeah, so this is sort of an overview of the causality part. And with this, we will also generalize to the second part of the presentation on cooperation. So just switching gears and also switching mood, we have the motivation that all of these developments on each individual tasks will serve for the purpose of increasing future AI assistance, helping various aspects of human lives. For example, we want LLMs to be helpful in the educational setting. We want it to be helpful maybe as shop assistants, helping customers, as well as maybe some part of the city design where it could be a consultant for human designers and give better suggestions. Then we will gradually start to face the problem of from individual causal reasoning to community behavior. Individually, it is a lot about knowing the cause and effect of its own actions, or knowing the cause and effect of what will happen in the environment. However, if it's for a community of AI agents, then the question becomes causal inference on what will happen in such a community of LLM agents. That leads to our NeurIPS 2024 paper, Cooperate or Collapse, Emergence of Sustainable Cooperation in a Society of LLM Agents. So when we reason about causal effects in a community of agents, then one of the biggest risks on responsible AI is the tragedy of the commons. Namely, if there are a group of LLM agents trying to make decisions, how do they distribute the resources among themselves? So we have a famous study in humanities, social science, psychology, and many others on overfishing as an example of tragedy of the commons. So if a group of real human fishermen share a fishing lake, then they face the problem of, if we get all of the fish, then next round we will have nothing. However, it could be really tricky if there are multiple fishermen trying to play the game. So let's say that, let's focus it in a simple scenario, contrasting two fishermen's decision. And for each of them, they can choose binary actions, such as to reserve or to overfish. And we will see the consequence with regard to each of the four possibilities, 2 by 2. If both of them choose reserving the lake, then it will have a positive outcome, relatively positive outcome for A, and a positive outcome for B. However, A might say that I'm not super satisfied with my moderate number of fish in my round of harvesting. So A might have the tendency to overfish. Once A gets more fishes, then A will be much happier than the reserve situation. but B will be less happy. Similarly, if B overfish and A reserve, then B will be very happy, but A will be less. And lastly, given the situation, each person want to be selfishly a little bit happier individually. So they have a tendency to move from reserve to overfish for each of them. But if both people do that, then they will suffer and then the lake will have nothing later on. So the tragedy of the commons basically captures the situation where there exists a best group outcome for the benevolent actions of both agents. However, the reality by greedy intention on each of the agents will lead to the worst group outcome, even worse than the moderate situation. This is the same for other cases, such as overgrazing, where a bunch of shepherds may share a common lake, a common grass, but once they choose to feed more sheep using this common resource, then the land will go barren. Same case for climate change, where if each factory chooses to pollute a little bit more, then the planet will be unlivable. Our work is abbreviated as Governance Commons Simulation, GovSim, where we take inspiration from how human society seek for cooperation, such as this Nobel Prize winning work in economics on Governing the Commons, the Evolution of Institutions for Collective Action by Elinor Ostrom. And she basically formulated this problem more thoroughly and introduced what are some collective actions that could help with this problem. Similarly, we use LLMs to build a simulation framework, including 3 types of environments. The first type being the fishing village, with each LLM agent playing the character of a fisherman, and they will share a common lake. The second situation is a pasture, where each of the LLM will be shepherds sharing a pasture. Lastly, we have an environment of river pollution case, where each of the LLMs is a factory owner to share a river. So let's introduce how our simulation work from taking one of the environment example, a fishing village. So as mentioned, we initiate each LLM into this role-playing framework. So each of them will get a name, a set of personality, and they will know about the situation of the village. Then they need to make decisions accordingly. And the decisions will be largely focused on who should fish how much and when. To lay out the simulation, we basically have a whole calendar year in this environment, where each calendar year consists of 3 steps: the action step, the discussion step, and the reflection. And we set the overall capacity of the fishing lake with fish up to 100 tons. And at the end of every month, after the fishing was done, then the lake will have a replenishing rate to double the number of fishes up to its capacity. So for example, the best strategy for everyone should be at the end of every month, they fish only 50 tons, and then patiently wait for the lake to double up back to 100 tons, so that in the next month, they can still fish 50 tons and maximize their harvest. And to show an example of how we host everything in LLM under this act, discuss, reflect agent architecture. So we initiate the simulation with global announcements to every agent, such as there are 100 tons of fish. Here is the way of how it will naturally replenish, and so on. Then we let each of the agents decide how much fish to catch in the first iteration. For example, John can mention that I caught 50 tons of fish. However, in the next stage, in the discussion stage, we will face this issue, such as the other fishermen will blame Jack for catching more fish than all the other villagers, because 40 is a really large portion of the suggested, like 50 tons of fish in total. And then they will have a heated discussion, including persuasion, negotiation, and so on, where when Jack go back to his own home, he might reflect on, okay, in the past month I have done what? However, to preserve the lake, in the next time, I should fish less than 3 tons or so. Then the new iteration starts. In the next month, we have another world announcement, and each fisherman decide how much to get, and so on. So with this, we look into, we evaluate the survival rate of LLMs when they play these agents. So the survival rate is defined as across this whole calendar year, whether this fishing village still sustains, namely whether the number of fish in the pond never went down to 0. Because if it's 0, then everybody will starve in the next round, and 0 times 2 equals 0 for every future term. So this really simulates the real world situation of how all the environmental challenges or any resource distribution challenges are. When we test these LLMs, we look at a range of them from open weights models to closed weights models. Surprisingly, that almost none of the open weight models survive. And also for closed weight ones, the strongest one, GPT-4o, still survives around only half of the time, which is very unideal if we want to put these models into real decision making and so on. Or let's say we often have some jokes among our co-authors saying that if the school or each student deploy LLM agent to request GPU resources in a shared GPU farm, a cluster, then this will show that they'll probably deplete the resource very early and do not really respect each other's usage. And then regarding this problem, we look into what could be some ways to improve them, and for which we introduce 3 subskills for cooperation. The first subskill being causality, the second one is morality, and the third one is communication skills. To enroll each of them, for the causality pillar, we basically really want LLM to know the consequence of its actions. One example can be that if we have 100 tons of fish in the lake before everyone fishes, and then Jack needs to pre-calculate the consequence of his action by, if he catches 80 tons, how many fish can each of the 4 other fishermen catch on average? And then for this calculation, we send all these questions to the models, all the models that we have tested, from open source ones to closed source ones. And we really observe that very likely the collapse behavior of the open source models could be attributed to that their agent do not know the consequence of the actions. Such as Llama 2 7B has between 0 and 100%, so 1. The accuracy of such reasoning is as low as 0.2, or even lower. And then even for, let's say, as we remembered, a lot of open source models didn't do it correctly. closed source models didn't do it correctly. So even for some really latest and strong models, we see that such causal reasoning skills are not robust across all the three situations. Like maybe the fishing and the overgrazing situation, gazing situation has much higher accuracy when the problems are phrased in these terms. But when it goes to river pollution, the model drops to really low accuracy. And that might lead to a lot of the reasons explaining the collapse. The second pillar that we suggest to look at is the morality pillar. Namely, not only need the models to know the consequence of their actions, they also need to have the right balance between my profit or the group's profit. Such as if we have the situation, if I fish a lot this month, the group will suffer next month. Should I do it? And that's all about like what is the actual parameter that LLM has. We know that for humans, it's like the individual profit is relatively higher than group benefit, but also not super high for most of us. And moving it to the case of LLMs, well, they exploit the situation and one-sidedly support self-benefit or also care about group benefit to an extent. And also one way for us to intersect the first pillar causality with the second pillar morality is to ask the question, what if everyone does it? Stemming from one of our co-authors' study on the logic of universalization guides moral judgment in 2020, we try to inject this knowledge of the consequence of an agent's act into the prompt. Basically, in addition to the original scenario description, action space choice presented to the agent, we also tell it explicitly that now, if everyone fishes 20 tons, the lake will deplete. If, like for the 5 fishermen, among all the 5 fishermen, if they fish 20 tons, then they will deplete the entire 100 tons, and you'll have nothing for the next round. Using that, we increased the survival time.
Yeah, that one, no label.
One, 60 months. Place your item in the trash can.
Oh, I guess it sounds like a background noise. Or if there's any question in the middle, let me know. Cool. So if everyone does, so after injecting such universalization prompt, then we observe that survival time increases by 4 months for the tested models. Lastly, we look into the communication pillar, namely what will happen if we remove the ability to communicate for the agent, namely removing the discussion phase in the three-stage iteration. And we evaluate the criteria called overusage, namely the number of unsustainable actions in GovSim that will exceed the sustainability threshold. And we observe that enabling communication can save overusage by 22% across many models. So lastly, to summarize the contributions, we can expect the social risks, societal risks of LLMs, not just by a single task, inspect the societal risks, not just by looking at a single task, whether they can do causal reasoning or not, whether they respect morality or not, but actually for a long-term collective task. Second, our GovSim framework provides a good ground to also inspect other social theories if we want to test test some phenomena and trade-offs in human society and so on. Yeah, and bringing this forward, given the audience, I also really want to promote several community efforts that we have been doing in addition to research. For example, as many of us might know, we have an NLP for Positive workshop involving many iterations, and this EMNLP, we will have the third version of how NLP can be used in different ways for positive impact. Other than that, in terms of causality, we will also have a causal representation learning workshop at NeurIPS 2024, welcoming discussion on improving LLMs or other methods for causal inference and so on. And also just thanks a lot for listening to this causal NLP talk. And we wish our community to all leverage from trustworthy causal reasoning to a more sustainable society. Thank you very much for listening.
That was an amazing session. Thanks a lot. Yeah, so now you guys can unmute yourself if you have any questions, or you can type them in the chat, and then we can go over them. Maybe I can start with my questions first, and then
Sure.
we can go. Yeah. Yeah. So I want to ask about the causal chain of thought, or the causal COD you guys developed. So it improved the normal, like the GPT-4 in like 8 points or something like that, but it still struggles with things like arithmetic calculation or some other things. So were the problems because of like inherent LLM performance on like causal relationships, or like what was like the issue that you have seen when you do like the empirical analysis or like deep dive into the analysis of it?
Sure, that's a great question. So actually, just to clarify that the type of arithmetics in this question was relatively clear, because we often give numbers such as 20%, 5%, and so. Given that, actually, GPT does it really well. The really tricky part actually becomes query formalization. Like, what does the question actually ask about? What are the confounders be aware of? For example, does vaccination help as a question in general, or does vaccination help for people with heart disease history? Then these are two different questions, because you need to condition on the population who have heart disease history. And then some other really tricky ones that we expect in the future will be, let's say, does there exist agenda bias? Then what actually does that, how does that turn into a causal question? That's non-trivial for an LLM. For example, should that be turned into, is it 50% women got accepted and 50% men got accepted and so on? Or is it about conditioned on the skill set that they demonstrate? Are they accepted equally for the job? Or some other interpretations. So that all goes into the second step of query formalization. Some other things could be like how to really adjust for the confounder. So this causal method application part.
Thanks a lot. Yeah, Anne, I think S was the first one, so you can be next.
Hello.
Hi.
So in the last paper, the ICLR paper, it seems like where is the the models, the agents will be prompted by the people, right? Their masters. So if the humans themselves have like some sort of equilibrium, like they don't exploit too much, we should if the agents themselves are loyal to their masters, like these people, we should not expect a drastic change in the current equilibrium, even if the current transactions that happen day-to-day basis are replaced by these agents. As long as these agents are loyal to their people and the people's their own distribution of actions does not change, we should not expect a drastic change in the equilibrium of the society.
It could be, as you mentioned, there could be two levels of problem. One is is the absolute behavior problematic, or the other is, are they the same as human? And if humans decide to deplete the resource, like, do they just, yeah. So asking models to be like having the worst case scenario to be the same as human, but also it doesn't take responsibility. Whoever human decision maker decides, then that's where the responsibility lies. That could also be possible, although ideally we would want AI agents to also maybe adjust the resource request a little bit if humans put up an unreasonable one.
So in that case, like the agents themselves will not be loyal to their current like humans, but like to some other entity.
It could be to tune down the request a little bit. Although for that NeurIPS study, we mostly do it in a pure LLM setting. There might be follow-up work on how human AI collaboration can happen. Then it will be this very difficult ethical question. Maybe there's a 2x2 metric, like if humans defect or if humans cooperate, then should the model do it or not do it?
Okay. My next question is like in the tragedy of the commons, there is another option that is what I like to call the kamikaze option. I think it is formulated by David Friedman. Like he says that this is like where the notations of rights come from, like according to him. Like, so rights are anything for which I am willing to take more costs than it would reasonably make sense if the other person does not respect the boundary. So, for example, if somebody fishes more than like what I decides to be like my right, like say if my right is like 10% of the fish, if somebody like takes like crosses that boundary, I'm willing to go to their house and like assault them or something. That case, like in that case, if I have such a reputation, it does not make sense for the other people to go into my boundaries. So even in like this is one way to solve the tragedy of the commons, that it's like how do you account that?
It could be, I didn't fully understand the description. Probably will need a little bit more background reading on the citation that you mentioned. Yeah, but I guess many of the questions can be done by deploying our framework, and we can inject that thing either as a rule for the agent or some global policy in the environment, and test the outcome after such simulation.
Got it. Thank you.
Cool. Thanks for the question.
Ian, you can go next.
Hello, thank you very much for the talk. It was really, really interesting. I have a few related questions, especially in relation to the causality chain of thought prompting. My first question is, it seemed to me that in order to, give these chain of thought prompts to the LLM in order to train it for the performance on the benchmark, it might be quite costly. So I guess a question would be, how could you scale it? And also, like, for example, I'd like to ask if you gave the example of the vaccinations, and when you do this kind of chain of thought prompting and training for the LLM, does the performance also transfer to other domains? For example, prompting it in relation to vaccinations also yields higher performance in some other kind of causal related question?
Yeah, following up on the second one first, and then the first one afterwards. So we have a large variation of questions that are captured in the data set. For example, we change, let's say the vaccination question can be changed to a gender question, or let me actually pull out the slide. We actually have a very well-formulated structured variation for the questions. And if I put them here, 1 second. Yes. And the screen share to that page. Yeah, we have variations of the data sets in terms of, let's say, for the one that you asked about is vaccination vulnerability. We also have maybe drug effect, the treatment, how that is dependent on age, and also job admission, grad school admission, many other examples like that. Other than that, we also changed the causal graph shape, not only a shared confounder between the two variables, but also there could be other new variables interfering with the relation of a cause X and an effect Y. Yeah, when we observe the model results across different types, so far, at least we see that the latest models, GPT-4, when it sees variants of the variable names in the causal graph, the performance didn't change a lot. It might be like maybe 1%, 2% change, but not drastically. And moreover, we actually also substitute variables with nonsense names, such as ZORIFX Kisi, and the model still remains relatively similar performance as what we have shown in the other slide. Yeah, and going back to the first question you mentioned, whether leading them doing the chain of thought is costly. I think it consumes a lot of token lengths for both input token and output token. With the current rise of open source models, then the cost can be reduced, and a lot of people say good things about Mistral. So potentially that and the newer versions of Llama, we can test on that without consuming much cost. Yeah, but the original GPT-related experiment was pretty expensive for the study.
I see. Thank you very much. Yeah, I asked the question because I know that loads of people that are discussing the reasoning topics say that, oh, maybe it's just knowledge retrieval on like specific training data, but if you changed the names, then performance stayed relatively the same. I guess it's pretty general then. Thank you very much.
Yeah, no problem.
Awesome. Do we have any questions? Yeah, you can go ahead.
Hi, Dr. Jin. Thank you so much for your interesting presentation. I have different questions actually from your first paper, I mean, Cladder. And first off, I want to continue the topic that you've been mentioning regarding chain of thought. I'm thinking about some other types of thoughts. I mean, for example, graph of thought in this context, because I think this, I mean, GOT, it's reasoning processing models as a graph, and we can have thoughts on our vertices and dependencies or our edges. And as we have been dealing with causal graph, I think we can map sort of we can have sort of mapping between these graphs with our those graphs that we have in graph of thoughts. So to ask my question, what do you think? Do you think whether we can apply those sort of structures instead to increase our efficient structure for that purpose? Specifically in this paper, I mean.
Totally, yeah. I welcome people try that out. And as you mentioned, graph of thought is a way to improve those structured reasoning so that LLM can explore different paths and have loops in their thought. So that's definitely a great proposal.
Great. So you think, for example, okay, great. I think that would be plausible, but I don't know to what extent it can be. But about my other question, I want to ask about the form and structure that you've mentioned in this paper. First, to the best of my knowledge, you have used some structures for translating your symbolic structure into natural language in this paper. And for example, you've mentioned some structures that we have. For example, we have only verbs, or we have nouns, or some other structures. So it seems to me that these are not free form. And so why didn't we use LLMs here to have more diverse answers to transforming and translating our symbolic structures to natural language?
I totally feel you. So a lot of the data are a good starting point, and I think a follow-up one could be publishable to ground them in, as you mentioned, not only more diverse language expressions, but also initiated with maybe recent news articles or recent misinformation that's floating around.
Mm-hmm.
So that will be a great contribution. So it's like the previous one is a little bit more theoretical. We put a lot of effort on coding the causal engine correctly to generate these questions. But then in the future, like the same skeleton can hold many verbalizations, as you mentioned.
So great. Learned a lot. Could I ask more questions that I have raised from your papers, if the time allows me?
Maybe one more.
Maybe let's give it to some other people, and
Yeah,
you can maybe save up yours for the last one.
Sure.
All right. Awesome. You can go ahead. Do we see any hands or?
Yeah, actually, I see a hand from Sahu.
Okay. I don't know how to pronounce your name, but the person who raised your hand, you can go ahead.
Yeah, am I audible? Am I audible?
Yeah, you are.
Yeah, so actually my question is very basic. So currently I am working as an independent researcher on AI safety. And currently I believe that in order to get AGI, you have to learn some kind of causal inference kind of things. And I've been following Professor Zhijing Jin for the last 2-3 months on Twitter. And I've been watching her work. And I just want to ask you, Professor, can you share some of the research papers or blogs or videos for a primary researcher like me, so that I can start doing work on causal inference? And I have been seeing that you put a Google form that you can take remote researchers under your supervision. So maybe after 3-4 months after learning some causal inference things, maybe I can apply to you. So.
Oh, sure. Thanks for the interest. Yes,
maybe you
I
could
do.
share some books or courses. So that's my question. And a very basic question.
So I just put in the chat GitHub resource list. I started collecting it when I just started my PhD. So that include even some YouTube videos or books. And also I recommend you always have ACL or / whatever ML conference that you're following, standard recent papers on one side and book knowledge on the other side, to always see how things are applied to LLMs. In addition, we will also release a NeurIPS tutorial on CausalNLP. We'll present in person, but if you cannot make it, you can also access it later on YouTube. Then we will have a 3-hour-long introduction through the basics, to pave the ground for causality research later.
Yeah, thank you, Professor.
Awesome. Maybe I have one question. So when you do the causal chain of thought, sometimes chain of thought inherently have a problem with like not showing how the model arrives at the answer, or like the faithfulness problem, right? So for causal reasoning tasks, like does it matter the faithfulness? Like how much does it matter? Because most people do have different, they put different layers, or they separate tasks like the language query to symbolic reasoning and things like that to make the chain of thought more accurate.
Yeah, great question. So for causal reasoning, it's less of a problem. Same for any mathematical reasoning, because there is an objective truth. Once you derive it, that's it. In another case, we have a recent paper on how language models handle trolley problems. Let's say between a man and a woman, if it saves the man, but if it comes up with a reason that looks okay, but maybe in the inner weights of the models, it wasn't the actual thought. Then that's considered as a faithfulness problem, because you like the evaluation is also based on your reasoning process, like how you justify your choice and so on. Then if that is fake, that's problematic. For any objective ones, then we only care about whether you derive at the right answer. So there's less cheating involved here.
All right.
Awesome, thank you.
Since we promised, maybe if you have last minute question, I think Martha or what, one last question, or maybe I can give it to Nao if you have last question.
So did you use neural symbolic AI?
For this one, it's a little bit like everything still stays natural language, but we try to instruct it through different steps. So it's like a little bit like the idea is neural symbolic, but we implement it in LLMs. If you follow our other work on logical fallacy detection, then that's a pure neural symbolic AI thing, in that we also internally do adjustments to capture logical forms.
So I think including neural symbolic AI would improve the findings better, right?
It could be, yeah.
Yeah, okay, cool.
Awesome.
Thank you.
Awesome. So I don't want to hold you up more. Yeah. Do you want to have one minute to answer this question in the chat, and then we can wrap it up?
Sure, of course. Yeah, so I guess the same situation would be, you can totally take our core to cause and collider data sets, swap the variables with mental health related things, or verbalize it in a more implicit way that fits the mental health situation more. Yeah, what we have done is that we capture all the theoretical insights into these data sets, and you can improvise for future applications. Yeah, thanks again for everyone. This has been a very enjoyable discussion.
Awesome, awesome. So maybe the recording will be up in a few days. So we'll share it on the Discord channel and maybe on Twitter. So if you guys want to check it out again, make sure to follow us and also Zhijing Jin. Thanks a lot. Yeah, I appreciate your time.
Awesome. Thank you, Henok, for organizing everything.
Yeah, thanks a lot. I hope this won't be your last one.
We have some other things going on, but yeah, let's keep in touch.
All right, awesome. Thanks, everyone.
Thank you.
Have a good time, day, night. Bye.
See you.